So in this last lecture, we're going to talk about how to adjust the composition of the final LC3 cement to get the best performance. What we're going to talk about here, we're going to talk about the impacts of sulfate, because this is the most important thing to adjust, and then how you get a good sulfate level for your LC3 cement. And then after that, we're going to talk about the impact of alkalis and illustrate why LC3 cements are very good for controlling alkali-silica reaction. So here we see the heat evolution of a typical Portland cement. And what's important to realize is that the main peak here, this is the reaction of the A-light. And because A-light is the most important phase in the cement, you want the A-light reaction to occur properly. And this means that the reaction of the aluminates should occur after the reaction of the A-light. In fact, in a good, well-controlled Portland cement, we have first of all a very fast initial reaction of the A-light, during which sulfate absorbs on the surface and slows down its dissolution. Then, after the A-light reaction, when the sulfate has been consumed from solution, we will get this small hump here, and this actually corresponds to a second formation of ettringite. What happens is the sulfate has been absorbed in the calcium silicate hydrate phase, and this is then released to form more ettringite. And only later on do you get the formation of the AFM or monosulfate phase. So our understanding of the level of sulfate goes back to the work of Lurch in the 1950s. And this shows here the classical idea. If you have a very low sulfate content, such as this yellow curve here, then the reaction of the C3A occurs before the A-light, and the A-light reaction is dramatically suppressed. You see here now is the A-light reaction, and you see it's much lower than in the properly sulfated systems. In his time, cements contained quite high amounts of C3A. So in what he called a properly sulfated system, the green system here, we have the A-light peak, and then we actually have quite a big aluminate peak. As I say, this would be quite unusual today because cements generally have much lower C3A content. And finally, with a level of 3.5, which would be roughly what you'd have in terms of sulfate to C3A ratio you'd have in a cement today, he in fact reported a low peak at 50 hours, which was the monosulfate reaction. So what's important here is that in systems with calcined clay that bring extra alumina, we need to adjust the sulfation. So we can see that in the next slide here. Here we have systems of LC3, and the turquoise curve here is if we don't add any extra gypsum to account for the alumina in the metakaolin. In this case, we see the A-light peak occurs as normal, but then after the alumina peak, we have this very sharp downfall in the heat evolution, which corresponds to suppression of the latter part of the A-light reaction. And when we properly sulfated, we go to this green curve here. We see now we have the alumina reaction occurring nicely after the A-light peak. If we go a little bit higher in terms of sulfate addition, then we come to this light green peak curve here, where the problem now is that this alumina reaction is occurring a little bit after 1 day, and therefore you're not getting the full benefit also of the reaction of the aluminate phase. And we can see the impact of this on strength. Here we see the relative strengths compared to the OPC system. In the system with no sulfate adjustment, the 1 day strength is only 40% of the OPC, whereas if we properly adjust the sulfate, then we go up to a 1 day strength of 65% or 70, even nearly 70% of the reference Portland cement. It's also important to realize that these overall levels of sulfate here are well within the levels of sulfate allowed in the standards. So it's not an excess of sulfate. So the second thing we want to talk about in this lecture is the impact of alkalis. And as with all pozzolans, you need a certain level of alkalinity to get your calcined clay to react. And if you don't have enough alkali in your cement, then the early strengths may be quite low. And we can see that in this graph here from a study in our lab, where we had quite a cement with a very low alkali content. And now we can see the effect of additional alkalis, and this very, very much improves the one-day strength. When we come to later strengths, they're all about the same. In fact, high alkalis can have a detrimental effect on the later strengths. So in this system, we probably want to be somewhere here with a alkali level of about 0.8 or 0.9. Now, some people have expressed concern that if we have these relative higher alkali contents, this could lead to alkali-silica reaction. But it has to be remembered that the alkali-silica reaction is very much responds very, very well to the presence of SCMs which contain alumina and silicate. So that's to say fly ash, slag, and of course calcined clays. And these are in fact the best method to avoid ASR. So how does this work? Well, first of all, we need to understand this concept of equivalent alkali. This is really just bringing the potassium into the system to the same molar basis as the sodium in the system. And people specify low alkali cements with an alkali equivalent less than 0.6, claiming that this will prevent ASR. But in fact, this is not a reliable method to prevent ASR. Much field testing and experience with large structures such as dams shows that this doesn't work in the long term. It's only an effect on the kinetics of delaying the reaction. On the other hand, when you have alumina silicate SEMs, these have two actions in the system. The first action is that the silica lowers the calcium to silicon ratio in the CSH due to the pozzolanic reaction. And here we can see some results from the thesis of Theo Chappé, where the addition of 15% either metakaolin, which has silica and alumina, or silica fume, which only has silica, were both effective in bringing down the alkali concentration in solution and so the pH. We can see that the alkalis here are about 1/3 of the reference system. But that's not the end of the story, because if it was only a question of lowering pH, then we'd really be in the same kind of system as in low alkali cements. It's really then a delay rather than a prevention. We have a much more effective way of controlling ASR, which is due to the alumina. So this was also shown in the work of Theo Chappé, that the direct presence of alumina in solution absorbs on the surface reactive sites of the silica and really inhibits its dissolution. So here we have pictures of reactive aggregates stored for 1 year in alkaline solution. Here we have just an alkaline solution on its own, and you can see the very extensive degradation of these alkalis, whereas on this side we have the solution with just a low level of alumina in the solution, and you can see the dissolution of the aggregate has been dramatically reduced. And this then relates back, as I said, to the alumina in solution. Here we can see poor solution compositions in LC3 systems, and we can see how with the kaolinite content in the calcined clay, then we have a dramatic increase in the level of alumina in solution. Here we have about 20-30 times the alumina in solution than in the reference system where we've added just quartz. So this will be very effective in stopping ASR. It can be really a long-term reaction because we have this reserve of alumina. We have this reserve of alumina in the unreacted metakaolin, but we also have a reserve that's in the CSH. Because of this high aluminas in solution, we can see the alumina to calcium ratio in the CSH, as shown by these points here, very much increases as we go to higher kaolinite contents in the calcined clay. And finally, we can see this in terms of accelerated testing. So these are accelerated tests done at 40 degrees C, and also they're done in simulated pore solution, which means you get no exhaustion of the alkalis due to leaching, as you do in many test methods. And we have all these LC3 systems down here. These are the reference Portland cements. You see they are expanding very dramatically, both with the reactive aggregate and the less reactive aggregates. But all these LC3 systems, even up to 3 years, which is the duration of the test so far, are showing absolutely no sign of reaction. So just to summarize this last lecture, what we've looked at is we've stressed the importance of adjusting the sulfate levels in the system to account for the alumina coming from the calcined clay. We've also looked at why it's important to have a correct balance of alkalis to get a good reaction from the calcined clay. And finally, we don't need to be worried about having a slightly higher level of alkalis, because the presence of calcined clay is extremely effective in controlling alkali-silica reaction. In fact, it's more effective than low alkali cements. So that's the end of this small series. I hope you've enjoyed it, and if you want to find out more, please don't hesitate to get in touch with us.